All right, in the second part here, section 2, we're going to look at the properties of waves. The previous one we had looked at what is a wave. So we'll look at those different parts and be able to have the skill of labeling and knowing which part is which on a wave. So can you describe a wave? For a water wave, one way might be to tell how high the wave rises above or falls below the normal level. This distance is called the wave's amplitude. The amplitude of a transverse wave is 1/2 the distance between the crest and trough, as shown in figure 6a. In a compressional wave, the amplitude is greater when the particles of a medium are squeezed closer together in each compression and spread farther apart in each rarefaction. So they were just talking about the distance. So the wave, here's that kind of that rest position here too. The amplitude is that distance from rest position to a peak, or how tall from rest to peak or rest to peak. Amplitude and energy. A wave's amplitude is related to the energy that a wave carries. For example, the electromagnetic wave that makes up bright light have greater amplitudes than waves that make up dim light. Waves of bright light carry more energy than waves made up of dim light. In a similar way, loud sounds waves have greater amplitudes than soft waves. Loud sounds carry more energy than soft sounds. If a sound is loud enough, it can carry enough energy to damage your hearing. As you see in figure 6b, when a hurricane strikes a coastal area, the resulting water waves can damage almost anything that stands in their path. Large waves caused by a hurricane carry more energy than small waves or ripples on a pond. And there's those other words that we're looking at, being able to label. The very peak of a wave is called a crest. The very bottom of that valley is called a trough. And then your amplitude obviously was that distance from rest position to those peaks. All right, and we'll read a little bit here too, but you can see that the next thing we'll look at too is the wavelength, or the distance from the top of one wave to the peak of another wave is the length of a complete wave. The devastating effect that a wave with a large amplitude can have is seen in the aftermath of tsunamis. Tsunamis are huge sea waves that are caused by underwater earthquakes along faults on the seafloor. The movement of the seafloor along the fault produces the wave. As the wave moves toward shallow water and slows down, the amplitude of the wave grows. The tremendous amounts of energy tsunamis carry cause great damage when they move ashore. Look at wavelength here. Another way to describe a wave is by its wavelength. For a transverse wave, wavelength is the distance from the top of one crest to the top of the next crest, or from the bottom of one trough to the bottom of the next trough. And we saw that up in here too. Crest to crest, or trough to the next trough over here. For a compressional wave, the wavelength is the distance between the center of one compression and the center of the next compression, or from the center of a rarefaction to the center of the next one, shown in figure B. It's hard to see kind of in this example here too, but kind of this light area to the other light area is the length of one compressional wave as you use this thing to push the air together. Or it's from the darker band to the next darker band here. Electromagnetic waves have wavelengths that range from kilometers for radio waves to less than the diameter of an atom for X-rays and gamma rays. And we'll get into EM waves in a week or so here too. But this range is called the Electromagnetic Spectrum. And that's what you can see this little diagram over here. And then it shows the distance of the wavelengths. You can see as it goes down, they start getting a little bit closer and closer and closer and closer. Radio waves have very long wavelengths. and down to the X-rays and gamma rays, as they said, which are very, very short wavelengths. All right. So the electromagnetic spectrum, visible light is only a small part of the electromagnetic spectrum. It is the wavelength of visible light that determines their color. For example, the wavelength of red light is way longer than the wavelength of green light. You can see that one because it's right here, and that's higher up on this scale. Just like the colors of the rainbow, longest wavelength is red. Shortest is going to be the one that's closer to the bottom of the scale, which is your blues and purples. Frequency. The frequency of a wave is the number of wavelengths that pass a given point in 1 second. The unit of frequency is the number of wavelengths per second, or hertz. Recall that waves are produced by something that vibrates. The faster the vibration, the higher the frequency of that wave. It's a sidewalk model. For waves that travel with the same speed, frequency and wavelength are related. To model this relationship, imagine people on two parallel moving sidewalks at an airport. One sidewalk has 4 travelers spaced apart 4 meters apart. The other sidewalk has 16 travelers spaced 1 meter apart. Now imagine both sidewalks are moving at the same speed and approaching a pillar between them. On which sidewalk will more people go past the pillar? On the sidewalk with the shorter distance between the people, 4 people will pass the pillar for each 1 person on the other one. All right. So they're trying to make the point here that this one has more frequency. There's more people, they're closer together, just like the waves that they're showing here. Okay. On any given second, you're going to have, you can see here there's 1, 2, 3, 4 waves. And over here you have like wave, 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 wave. There's a lot more. They occur more frequently with a much higher frequency. Frequency and wavelength. Suppose each person represents the crest of a wave. The movement of people on the sidewalk is like the wave with a wavelength of 4 meters. For the second one, it would be 1 meter. On the first sidewalk, where the wavelength is longer, the people pass less frequently. Longer wavelengths result in smaller frequencies. On the second sidewalk, the wavelength is shorter, and the people pass more frequently. Higher frequencies result in shorter wavelengths. This is true for all waves that travel at the same speed. As the frequency increases, the wavelength decreases. I'm going to skip the color and pitch one here. I think we'll just kind of touch on this one a little bit too, but wave speed. You probably watched in a distant thunderstorm on a hot summer day, you see a bolt of lightning flash between the dark cloud and the ground. Do the sound waves or thunder produced by the lightning bolt reach your ears at the same instant you see it? If the thunderstorm is many kilometers away, several seconds will pass when you see lightning and when you hear the thunder. This happens because light travels much faster than sound does. Light is an electromagnetic wave that travels through air about 300 million meters per second. On the other hand, sound is a mechanical wave that travels through air at about 340 meters per second. Mechanical waves such as sound usually travel faster in a medium in which the atoms that make up the medium are closer together. Sound travels faster in solids than in liquids, and faster in liquids than in gases, because those particles are much closer together in solids. As we learned in our other unit, liquids are a little more spaced and gases have a lot more space. I think that's where we'll stop for this one here today.